coming to this problem. So here you are going to analyze the portal frame, which is loaded with a uniformly varying load as shown in the figure by using a slope deflection method. You're going to draw elastic curve, bending moment and shear force diagram. So this is a figure. So for this portal frame, you are going to analyze. So here A, B, C, D is a frame. Whereas for AB member and CD member, there is no loading given. Whereas for BC member, you are having a uniformly varying load, which is a 40 kilonewton per meter. So the span of this beam is 4 meters, whereas the span of AB and CD are 5 meters. And here for all the members, there is a different moment of inertia. For BC, it is I, whereas for the columns, that is AB and CD, it is 2I. So here in this case, there is no sway condition. Why there is no sway condition is, first one, there is no any lateral load that is acting here at this B portion or in the column of AB. And next step is, next thing is there is no uneven supports at A and D. So both supports are at the same level. Whereas A support and D support both are the same supports, that means fixed support. So there is no case of sway condition here. But when there is a different support condition, then there will be a chance of having a sway condition. And whereas for BC, it is a symmetric loading that has been given. UVL, that is uniformly varying load, that has been distributed equally in this BC span at the center. So therefore, there is no sway condition for this entire portal frame. So the sway here is 0. So this is how you're going to start analyzing your problem first. Whether the given the portal frame is having a sway condition or no sway condition. So here in this case, and one more thing is the moment of inertia is different for columns as well as beams. But the two columns are having same moment of inertia. So that means when we cut this entire frame at the center, so it should be like a mirror image. So it is reflecting like same mirror image. So whatever the span towards the left side it is having, the loading and all, the moment of inertia and the support conditions, the same is having in the right side also. So that means just I will say, so here when I cut this section at this point, you can just see, okay. So here in this, you're having a triangular load of 40 kilonewton per meter. And here also you're having towards right side 40 kilonewton meter. And towards at this B, there is no loading, no loading. And whereas this is 2I moment of inertia for AB, similarly, there is a 2I moment of inertia for CD also. And A support is fixed support, and here D is also fixed support. So that means it is a reflecting image. So therefore, here there is a no sway. It is a no sway condition. So that means here the delta will be equal to 0 for this AB and as well as CD also. So now you are going to start your problem. So coming to your step 1, you are going to determine the degree of the freedom. So for this, you can just see as A is a fixed support. So here you are not having any rotation and you are not having any translation. That means theta and delta are 0. Whereas coming to B, it is having a rotation at B, but there is no settlement at B. So that means delta is 0 at B, whereas theta is not equal to 0 at B. Similarly, C also, there is a rotation, but there is no displacement. That is delta C is equal to 0, whereas theta C not equal to 0. Similarly, at D portion also, as it is a fixed support, there is no translation and there is no rotation. So that means theta D equal to 0 and delta D equal to 0. Now you can say that the degree of freedom is 2, that is theta B and theta C. So here you are going to find the two unknowns, that is theta B and theta C. So coming to your next step, you are going to calculate the fixed end moments. So coming, as there is no external loading on this AB member and CD member. So therefore, moment about MFAB and MFBA, MFCD and MFDC all are equal to 0. No external loading. Whereas coming to BC, you are having a trapezoidal loading. triangular loading. So that is your uniformly varying loading. So for that, I'll just draw a figure. So here you are having a trapezoidal loading. So we have to take the fixed end moments for this. So for this BC, you are having a moment like this. So this is your MFBC moment. So which is minus 5WL square by 96. So which is in anti-clockwise direction. Therefore, it is written as negative here. And similarly, MFCB is 5WL square by 96. So which is in clockwise direction. So therefore, it will be represented as positive value. So here the loading is 40 kilonewton per meter and the span is 4 meters. So by substituting these values, you are getting MFBC is minus 33.33 kilonewton meter and MFCB is plus 33.33 kilonewton meter. So this is how you're going to calculate your fixed end moments. And now coming to your step 3, that is your slope deflection equations. So here the slope deflection equation is MAB is equal to MFAB plus 2VI by L into 2 theta A plus theta B minus 3 delta by L. So that means this is a fixed end moment and this moment will be equal to a moment due to rotation and 6A delta by L square will be equal to moment due to the settlement. So in this problem, as we already told that there is a no sway condition. So the delta will be 0 in this case. Okay, so therefore now the slope deflection equations will become like this. Only fixed end moments plus moment due to the rotation only. So you are going to substitute all these equations for all these 3 members, that is AB, BC and CD. So now the slope deflection equations. So by substituting MAB, the simplified equation will be like this. So here in this case, I'll just write down theta A is equal to 0 and theta D is equal to 0. So therefore, by solving this, you are going to get these values. So similarly here also, this one 0. Similarly, external moment is also equal to 0 since there is no external loading acting on it. Similar way, MFBC also. So here for MFBC, you're having a moment of 33.33, which is of negative value. And here you're having both rotations, theta B and theta C. So that is this equation. Okay. So similar way, in the next step also, you're having MCB. So MCB also, you're having a moment of 33.33 as your fixed end moment. And then theta C and theta B are there. And then MFCD, again, here you are having theta D equal to 0. Therefore, here there is no external moment and there is theta D is also equal to 0. So by substituting this, you are going to get in terms of theta C. Okay. Similarly, MFDC also. So here also there is no external, there is no fixed end moment for DC. And whereas theta D is also equal to 0. So these are your simplified equations. So by using all these simplified equations, so we are going to establish the equilibrium conditions for this entire frame. So now coming to your step 4, equilibrium conditions. So what are the equilibrium conditions here? So here you are having only 2 equilibrium conditions. So that is sigma MB equal to 0. So this is one. And here sigma MC equal to 0. So this is another equilibrium condition. So what are the unknowns here? Theta B and theta C are your unknowns. So 2 unknowns and 2 equations. So we are going to solve the problem. So this is sigma MB equal to 0. So that means MBA plus MBC moment will be equal to 0. So this is a simplified equation. So you are going to get this equation 1. Similar way, next one is sigma MC equal to 0. That means MCB plus MCD will be equal to 0. So by simplifying this, you are going to get this equation. So this is your second equation. So now solving these 2 equations for the unknowns theta B and theta C, you are going to get theta B is equal to positive value, whereas theta C is equal to negative value. So whereas theta B is positive means clockwise rotation, theta C negative means it is in anti-clockwise direction. So just we will draw the elastic curve for this. So this is your A, B, C, and D. So if you just draw like this, and when we or draw a tangent like this, so this is becoming in anti-clockwise direction. So I'm going to draw, sorry, I'm going to draw in this way. Okay. So this is also positive. So when we draw a tangent like this, so here you are getting a clockwise rotation. When we draw a tangent like this, here also you are getting a clockwise rotation. So that means theta B is equal to 15.87 by EI. Whereas here when we draw, so this is in anti-clockwise direction of theta C is equal to 15.87 by EI. So here also, so when we draw an elastic curve like this, so when we draw a tangent, so this is also theta C. So this is a C point and this is a B point. So this is a clockwise rotation of theta B. So this is an anti-clockwise rotation of theta C. This is how you're going to draw your elastic curve. Clear? For this frame. Now coming to the calculation of your final end moments. So by substituting these theta B and theta C in these equations following end moment equations, so we are going to get your final end moments. So these are your final end moments. MAB is plus 12.69 kilonewton meter. MBA is plus 25.39 kilonewton meter. MBC you are getting minus 25.39 kilonewton meter. Whereas MCB you're getting plus 25.39 kilonewton meter. Again, MCD you're getting minus 25.39 kilonewton meter. MDC you're getting minus 12.69 kilonewton meter. So these are your final end moments. So by using these final end moments, we are going to draw the free body diagram. Then you're going to draw the bending moment diagram and shear force diagram. So let's see how to draw a bending moment diagram. So for this frame, so these are the end moments, what we got it from the previous problem. From this problem, from the previous step. So I'll just draw the reactions first. So this is your A, B, C, and D. So AB, you are having a plus value. So that means it is a clockwise rotation of 12.69 kilonewton meter. And this is also a positive value. So which is clockwise direction, MBA also. MBC is negative. So that means it is in anti-clockwise direction. So which is of 25.39 kilonewton meter. And similarly, MCB, you are having a positive value. So that means clockwise. MCD, again, you are having anti-clockwise. So that means it is anti-clockwise direction. So this is again 25.39 kilonewton meter. And this is again anti-clockwise direction. DC is also, that is negative value. So that is 12.69 kilonewton meter. So this is related to the final end moments. So this is the free body diagram for this. Whereas coming to this external loading that is acting. So which is of 40 kilonewton per meter. So the span here is 4 meters. So when we take this only this external loading, so we should find the reactions. Okay. So I'll just take this part aside. We'll draw it separately. Okay, so for this, we'll draw the bending moment diagram first. So for this spans, so here you are having both 25.39, 25.39, which is in sagging in nature. So this is 25.39 kilonewton meter, and this is also 25.39 kilonewton meter. And one more thing here is, so here you are having 12.69, and here also you are having 25.39. So either you can draw from this side, if you are seeing, you can draw in this way, or from this side you are drawing, you can draw like this also. So I'm just drawing in this way. Okay. Similarly, here also you are having a moment of 25 here, and then here you are having 12.69. So tension side or compression side, both sides you can just draw. So this is 25.39 kilonewton meter, and this is also 12.69 kilonewton meter. One thing is, either you can draw this side 25 and this side 12.69 also, no problem. And here also it is 25.39 kilonewton meter, and this is 12.69 kilonewton meter. So this is due to the end moments. Now, coming to this loading, I'll just simply, external loading is acting at this point now. So I'm just drawing, this beam. So simple support. So this is fixed support. This is simple support. 40 kilonewton per meter. So here you are going to have the reactions. So this is 4-meter span. So now coming to, at this point, if you want to calculate moment, so first you're going to calculate the reactions RA and RB. So what are the reactions here? So RA and RB will be equal to total load by 2. So what is the total load here? Area of the triangle, that is 40 into 4 by 2. So that means RA and RB, you are getting it as 40 kilonewton, right? So when we want a moment at this point, at this center, at this XX, so moment about X will be equal to RA into 2 minus half into 40 into 2 into, so this distance you are going to write. So that means it is 2 by 3. So this entire thing will become 80 minus 80 by 3. So that will be around 53.33 kilonewton meter. So at this center, you are having a, so which is positive value of 53.33 kilonewton meter. So this is negative and this is negative. So this shaded portion will be your bending moment diagram. So this is simply how you're going to draw your bending moment diagram. And this variation will be equal to your cubic variation. Okay. So this is how you're going to draw your bending moment diagram. So what I have done is, we first draw the free body diagram. After drawing a free body diagram of the external moments that we got, final end moments. So for this, I have drawn the bending moment diagram. But there is an external loading on BC. So I just consider that beam to be a simply supported beam, and I found the reactions for RA and RB. After getting the reactions, I calculated the moment at this point. Why? Because moment at A will be 0, moment at B will be equal to 0. Just I calculated the maximum moment at the center. Why? Because it is a symmetric loading. So I just got the moment to be like this. You can just see the reaction. And this is how we got the momentum. So this is a bending moment diagram. Now coming to your shear force diagram. So how you are going to draw your shear force diagram? So these are the external moments, right? So coming to this external moments, first I'll draw the free body diagram for this. Okay, so this is your A, this is B, this is C, and this is D. So AB moment is clockwise. So this is 12.69 kilonewton meter. And BA moment, it is again clockwise. And this BC moment negative anti-clockwise. So 25.39 kilonewton meter. Whereas CB, it is clockwise. Whereas CD, it is in anti-clockwise, negative. So it is 25.39 kilonewton meter. And whereas for DC, it is again anti-clockwise. So that is 12.69 kilonewton meter. So this is a free body diagram of the moments representing. So after the moments getting represented, how you are going to draw the bending moment diagram, sorry, shear force diagram. So just I will take, so for the shear force diagram, span AB I am considering. So if you just consider span AB, so this is your span AB. This is A and this is your B. So which is having 25.39 kilonewton meter at B, and at A you are having 12.69 kilonewton meter. So just the span of this is 5 meters. If you just consider the moment about this point, okay, I'm just drawing the force to be like this in this direction. So this is force of BA, we'll consider, okay, or you can consider the reaction also. So for BA, so moment about A. So this is again at this point, it is in sagging nature. So that means positive value 12.69 kilonewton meter. So about this point, if you are writing FBA into 5, FBA into 5, this is in sagging nature. Again, this B moment is in hogging in nature. So that means minus 25.39 will be equal to 12.69 kilonewton meter. So that means FBA will be equal to 12.69 plus 25.39 by 5. So that means FBA will be equal to 7.62 kilonewton. So we are getting a positive value. So that means this direction is correct. So now, so as we are getting FBA, so now FAB should be in the opposite direction. That implies FAB plus FBA should be equal to 0. So FBA should be minus of FAB. So that means this will be in this direction. So that is your FAB, right? So I can just write down FAB is equal to 7.62 kilonewton, which is in this direction. And then FBA will be equal to 7.62 kilonewton, opposite direction. So same, this can be applicable for CD also. Why? Because it is a symmetric, right? So similarly, for CD span, FCD will be equal to 7.62 kilonewton, and sorry, I'll write it. I'll write it in the next page. So here FCD will be equal to 7.62 kilonewton, whereas FDC also will be equal to 7.62 kilonewton. So just consider this CD span. So for this CD span, this is a moment of 25.4 kilonewton meter, and this is a moment of 12.69 kilonewton meter, right? So this will be in this direction and this will be in this direction. So now coming to the span BC. Span BC, if you just consider. So this is a loading that has been given. So which is of 40 kilonewton per meter. So these are the supports B and C. And here you are having a moment at B as well as at the C. So the moments are 25.4 kilonewton meter. And this is also 25.4 kilonewton meter. We'll just see. Yeah, 25.39. That means 25.4 kilonewton meter. So here you are going to calculate your RB reaction and then RC reaction you are going to calculate. So coming to your RB and RC. So RB is equal to RC is equal to total load by 2. So the total load is half into 40 into 4. Again by 2. Total load is nothing but area of this triangle. So that will be equal to 40 kilonewton. So RB and RC both are 40 kilonewton. So now we got the reactions as 40. Now at this point, we need how to draw a shear force diagram. So the shear force diagram for this will be no need of moments acting. So only for this reaction. So as we are having equal moments at B and C point, so whether we take also, this both get compensated. So therefore, we are getting only the 40 kilonewton reactions. Due to these moments as well as due to this external loading, we are getting only the 40 kilonewton. So now how to draw a shear force diagram. So the shear force diagram will be, so this is A, B, C, and D. So for AB and BC, so you're getting this is negative and this, sorry, this is in this direction and this is in this direction. So both are having the anti-clockwise shear. So that means a negative value only. So that is 7.62. So here also CD, you are having in the, so this is also 7.62. And whereas for this, you are having a positive shear about this point. It is like a simply supported actually. So this will be like this. So this is plus and this is minus. So this is of 40 kilonewton. This is of 7.62 kilonewton. This is of 7.62 kilonewton. This is also 7.62 kilonewton. This is 7.62 kilonewton. And this is your shaded portion of your shear force diagram. And one more thing is for the columns AB and CD. So it can be positive shear and it can be negative shear also. Why? Because the way we are going to see is going to be a big thing. So if you see it from this side, so here at the CD, you are having in this direction. At DC, you are having in this direction. So if you are seeing from this point, it is in clockwise. So if you're seeing in this point, it is in the other direction. Therefore, this one for the column, we'll just shade the portion. No need of writing a symbol. So this is how you're going to draw the shear force diagram. These are the references. Thank you.